AI is supposed to save the planet, but is it quietly destroying it? We're told AI will optimize energy use and fight climate change, yet behind the scenes, AI's own environmental footprint is exploding. From massive, power-guzzling data centers to thirsty cooling systems, AI's green promises come with hidden costs. Imagine a technology marketed as green and clean, yet drawing immense electricity, water, and rare minerals out of sight. In this video, we'll uncover the hidden environmental cost of AI's green revolution and explore if AI can truly become sustainable. It starts with the narrative of green AI. Companies proudly tout their AI as energy efficient, climate friendly, even net zero. Tech ads show AI swirling with green leaves and earth images, promising smarter use of resources. We hear that AI will optimize power grids, cut waste in factories, and solve climate problems faster than humans. And indeed, AI can help, predicting weather for renewables or tweaking building energy use, earning its green label. At the same time, chip makers brag about new AI processors that deliver more performance per watt, so efficient they're practically eco-friendly. For example, Google even found its latest AI accelerator chips are 3 times more carbon efficient than those from a few years ago. All this builds a reassuring story. Smarter algorithms, efficient hardware, clean energy, AI that's gentler on the planet. But to see the full picture, we need to look beyond the marketing and dig into AI's physical footprint. So what is AI hiding? In a word, a massive appetite. An appetite for electricity, water, and resources. Every AI system ultimately lives in a data center, essentially a giant warehouse full of computers running 24/7. These data centers already devour a significant chunk of the world's electricity, and that share is growing. As AI expands, experts project data center energy use could double within just a few years. Why so much power? Training and running large AI models takes thousands of GPUs crunching numbers day and night. That means a constant draw of electricity, often produced by burning fossil fuels, unless the data center is on renewable energy. For instance, training the GPT-3 model once used about 1,287 megawatt hours of electricity. That is an enormous amount, roughly the power that 120 average US homes use in a whole year. And it didn't stop at training. Once deployed, those AI models run on servers for millions of users, adding to the energy bill. In fact, operating a popular AI like ChatGPT can consume so much energy that usage, inference, dominates its carbon footprint. Put simply, training is a sprint, but everyday AI use is a marathon that keeps drawing power. So, every time you chat with an AI or generate an image, there's a distant surge of electricity at some data center. Now, where there's electricity, there's also heat, which brings us to AI's next hidden cost: water. All those servers running hot have to be cooled, often by giant air conditioning and liquid cooling systems. Many data centers use water to carry away the heat, essentially evaporating it to keep AI cool. That adds up to a staggering thirst. A single mid-sized data center can drink around 110 million gallons of water a year, as much water as about 1,000 households use in a year. And the biggest AI supercomputing centers can guzzle up to 5 million gallons every day. Think of a small city of tens of thousands of people. That's the water footprint of just one huge data facility. Where does this water go? Much of it evaporates, dissipated as cooling towers try to whisk heat away from racks of servers. This means AI isn't just devouring power, it's quietly draining water from local rivers and reservoirs. Here's a crazy example. It's estimated that a single 100-word ChatGPT query can use up about half a liter of water through cooling. In other words, every lengthy question to an AI might be making a cup of water vanish into thin air. Multiply that by billions of queries and you start to see an invisible impact on water resources. And it's not just water and electricity. Building and upgrading all those AI machines comes with its own environmental toll. AI runs on physical hardware, chips, circuit boards, servers by the thousands, packed into data centers around the globe. These advanced machines require a cocktail of rare metals and minerals: copper, cobalt, palladium, gold, and more. Extracting those materials from the earth is anything but green. Rare earth metal mining can produce toxic waste and huge carbon emissions. Arrays for electronics often releases greenhouse gases thousands of times more potent than CO2 and generates toxic byproducts. For instance, refining metals for GPUs has been called exorbitantly high in environmental cost. Then there's the manufacturing. Chip fabrication plants use enormous energy and water themselves to make those tiny transistors. All that hardware doesn't last forever either. AI hardware gets upgraded frequently, often every few years as more powerful chips emerge. The old units become electronic waste. And e-waste is a huge problem. tons of discarded circuits, heavy metals, and plastics piling up. Globally, we dump tens of millions of metric tons of e-waste each year, and most of it isn't properly recycled. And the AI boom could make this worse. One study warns that generative AI alone might add another 1.2 to 5 million tons of e-waste by 2030. Imagine mountains of discarded servers and GPUs, hazardous trash that can leach chemicals if not handled properly. This e-waste often ends up in landfills or developing world dump sites, where toxic materials seep into soil and water. Let's tally an AI model's carbon footprint across its life. Training is the first big hit. Data centers run full blast for weeks or months to teach a model. That one-time push can emit hundreds of tons of CO2. GPT-3's training alone produced more than 550 metric tons of CO2. Analysts equated that to the yearly exhaust of about 128 passenger cars. Another comparison said a single large model training run can mirror the emissions from 125 round-trip flights between New York and Beijing. Then the bill keeps growing with fine-tuning and deployment. Every update spins those servers back up and adds a fresh layer of carbon to the ledger. Inference, the everyday use of the model, runs for years, and if adoption is high, it can dwarf the training footprint. Put it together, and the full life cycle, from building hardware to retiring it as waste, carries a hefty carbon price tag. One report summed it up plainly. Behind each intelligent answer sits an energy-hungry, water-thirsty, resource-intensive process we rarely see. Let's translate those numbers into daily life. We've already compared one training run to fleets of cars and long-haul flights. Now consider the efficient chips being hailed as saviors. They sip less power per computation, yes, but the embodied emissions of manufacturing wave after wave of new silicon can erase those savings if refresh cycles stay frantic. Microsoft reported in 2023 that roughly 2/3 of its carbon footprint came from the supply chain and hardware production. So even with better chips in use, constant upgrades can undermine the gains. Operational scale stacks on top of that. ChatGPT alone reached millions of users in months. One analysis estimated its monthly operations at about 260,000 kilograms of CO2, roughly 260 transatlantic flights from New York to London. That's a single service matching the carbon output of a small airline. The point isn't to shame AI out of existence. It's to remind us the cloud is physical, and its emissions rival industries we already scrutinize. If we ignore that reality, AI's boom could turn into a fresh climate liability, the opposite of its green promise. So, is this a doom story for AI and the environment? Not necessarily. We can still course correct by rethinking how we power, design, and deploy these systems. First, power AI with clean energy. Running data centers on renewable electricity slashes the carbon hit. Google and Microsoft already pledged net zero, zero waste footprints for their server campuses by 2030. When racks hum on solar, wind, or hydro, the emissions curve bends down fast. The hard part is making clean power available every hour. Operators are investing in big batteries, thermal storage, and smart grids so the lights stay green at night. Some campuses even overbuild renewables during the day, then shift excess into storage or neighboring microgrids. Second, make the AI itself more efficient. We can reach the same outcomes with leaner models and sharper math. Think smaller architectures, smarter search, and targeted compression that trims the fat without gutting accuracy. Researchers now champion green AI and publish the energy tab along with accuracy numbers. Model compression helps, pruning idle neurons, distilling knowledge into a compact student, or switching to lower precision calculations that still land the right answer. The payoff is real. One team pruned 90% of a network's weights, cut energy use by the same margin, and lost only about 0.5% accuracy. Knowledge distillation mirrors a large teacher inside a smaller, cheaper body, so inference runs cooler and shorter. Faster, leaner models mean less electricity, less waste heat, and lighter cooling loads. Hardware designers are in the loop too. Every new accelerator aims to deliver more work per kilowatt hour, and pairing those chips with efficient code squeezes extra value from every joule. Smarter scheduling closes the loop. Cue heavy AI jobs when solar output peaks or wind power surges, then idle when the grid dips. Third, extend the hardware lifecycle. Keep servers in service longer, refurbish instead of replace, and recycle components so the rare metals live a second life. If companies can reuse chips longer or repurpose older servers for less intensive applications, it slows the e-waste avalanche significantly. Experts note that refurbishing and reusing older hardware can cut e-waste almost in half. Better recycling programs can recover rare metals from old circuits, reducing the need for fresh mining. And designing hardware with recyclability in mind, easy to separate components, makes material recovery far more feasible. Finally, transparency and policy are critical. If AI companies report their energy, water, and carbon footprints, it forces accountability and sparks competition for efficiency. Governments are starting to pay attention. In the US, an executive order already nudges data centers toward cleaner energy, and lawmakers are drafting standards that measure AI's carbon and e-waste impacts. Such policies push companies to prioritize sustainability before regulations, or carbon taxes, do it for them. We might even see carbon labels for AI services. Imagine checking the CO2 cost of every query the way you read nutrition facts. Combine clean power, efficient models, long-lasting hardware, and transparency, and AI's footprint shrinks fast. We open with a hard question. Is AI's green revolution hiding a dirty secret? The truth is that AI does carry hidden environmental costs today, but it doesn't have to stay that way. AI could become a major source of emissions or a driver of energy efficiency. It depends on the choices we make now. If we demand and invest in sustainable AI, we can enjoy the benefits without it costing the Earth. The green revolution of AI succeeds only if we expose those hidden costs and innovate them away. We can have powerful AI and a healthy planet, but we need to align tech ambition with sustainability, starting today.